Well, welcome to Lecture 14 in General Relativity. I have titled this lecture Covariant Derivatives and the Christoffel Symbols. I don't think that's entirely accurate. I think it's more than that. The totality of this lecture. I'll cover the Christoffel symbols, the curvature, the scalar curvature, the whole deal. So let's get into it. So I'm going to begin with a derivation I found in the Geometry of Physics, an introduction by Theodore Frankel, and I'll probably follow that text for this lecture for a little while, about half of it. It derives a few things which Carrol, I would say, simply posits. Anyway, it has a different approach than Carrol, so I think it's useful to us. And so I'll begin with this calculation I found in Frankel. Here it is. Oh, and the book I'm talking about is this one here, Geometry of Physics, an introduction, which is a really delightful book. Anyway, suppose M is a surface in R3 with coordinates uv, the tangent plane. Well, we have these vectors, right? Partial derivatives of the position, basically partial derivatives of the patch with respect to the u or v coordinates, gives us the tangent vectors in the u and v directions. Then you can calculate the acceleration, x alpha beta, like that. And of course, because partial derivatives commute, you can either do x alpha beta or x beta alpha. And you may remember from studying elementary differential geometry that the acceleration, it doesn't have to be tangent to the surface, right? But of course the other, it's a surface in R3, so there's either the tangential direction or there's the normal direction. And so you can pretty much write the acceleration, right, in terms of two pieces. The piece which is in the tangential direction and the piece which is the normal direction. So you take the projection, essentially, you take the dot. This is the notation for this first part of the lecture. We're using this Langle-Ringle bracket notation for the dot product in R3. It's just that, okay? So this picks off we're assuming that the normals, that the unit normal has length 1. So this picks off the component of the acceleration in the normal direction, and then that puts it in the normal direction. So this is just the projection of the acceleration in the normal direction, and that's whatever else there is, which is, of course, the tangential piece. And what's curious at first glance is that we're calling the coefficients of the tangential piece by the symbol gamma, upper gamma, lower beta alpha, and that's the symbol we use for the Christoffel symbols. And you'll see that actually that is, I think that's actually a good notation here because, well, we're going to see it links up, all right? So the acceleration then, you've got two pieces, this piece and that piece. And first of all, by symmetry of the commuting partials, we get that these coefficients are symmetric in their lower indices, right? And we want to find a formula for those, okay? So let's get to that. So what we'll do, let me just go ahead and sort my papers. So what we'll do is we'll start by, excuse me, we'll start here by just noticing that when we take the acceleration and we take the dot product with the tangential velocity, the velocity, coordinate velocity, right? Well, that's going to get rid of the normal piece, and so you just get, the dot product of the coordinate velocities with the symbol here, but that is essentially by definition g gamma u, because this is the like the basis in the gamma direction, basis in the mu direction, so that gives you the component. So we're using a basis for the tangent space. We're using the partial derivative vectors, right? And I'm not saying these are normalized, okay? But so great. Well, then that gives us another formula, and so then Frankel introduces, I think he uses the slash, I don't remember. That may be him, that may be me. He may have done something like a comma or something, but anyway, let's just say we're going to make that definition that to lower the index we'll lower it to the end like that, and that way we won't have to write the g when the contraction over the g, we'll just write that, all right? So on the other hand, if we look at the product rule for the dot product, what happens there? Well, I don't know if you knew this or not, but the dot product has a product rule, right? And so we take the derivative of this, we get that inner product that plus x inner product with the partial derivative, the beta partial derivative of x mu. And of course those are exactly the acceleration, right? And that's the other acceleration, and sorry, it's bothering me. And so they're in terms of the symbol we just made up, it gives us this gamma beta alpha gamma again here like that. So this plus that, right? And remember that the dot product is symmetric, so it doesn't matter which one comes first and second. So we'll call that star, and we'll come back to it on page 2 here. All right, so what we got? Well, what we've got is that if we add together, so notice that we have this formula for the partial derivative of the metric here with respect to the coordinate. It's the sum of these two coefficients in that order, where we have like this, we do, you just have to see the pattern here, right? Beta alpha mu is repeated, and then over here, the last two are exchanged, all right? So that's the pattern, and we just do that 3 times over here, right? We do beta alpha mu, so we get beta alpha mu, mu beta alpha, so that gives us mu beta alpha, and then alpha mu beta, so that gives us this alpha mu beta over here. And then we fix the first index and commute the second two, fix the first index, commute the second two. And there's some cool cancellations that happen here. Remember, it's symmetric in beta alpha and alpha beta, so these two match up and they cancel, these two match up and they cancel, it just leaves you these two guys, which again are equal because of the symmetry of the first two indices, which gives you twice the coefficient, which gives you really twice the original coefficient contracted over the metric like that. There's a summation over tau here where it's just ranging from 1 to 2. And so there you go, that's the formula for the coefficients in terms of the induced metric on your surface in 3 dimensions. And that's not accidentally the same formula we'll see later in the abstract, okay? So that's pretty neat, and you know, I think I've seen this in differential geometry books before, but it hadn't really dawned on me, oh, it's the same thing as we'll do in the abstract, all right, in the higher dimensional manifolds towards the end of this lecture. And I probably should assign the derivation on page 229, which is problem 8.51 in Frankel. He mentions that Gauss looked at third derivatives of the patch, like this, and showed that their difference could be written as the contraction of a fourth order tensor, this type tensor, r tau alpha beta, gamma beta minus this other thing over here and that over there, where the r is defined in terms of the coefficients like that. That's exactly the same pattern that we'll see for defining the curvature later in this lecture. So anyway, Frankel claims that this calculation helps firmly connect the EFG-LMN to our current notation, right? So, of course, in the old language of Gauss, think about the first and second fundamental forms, and I don't have all that stuff. Like I don't have it firmly memorized or anything, so let me not try to be too dogmatic about what I'm saying here, but just to say that if you go through this derivation, if you're interested, page 229, let me just look it up here right briefly. So yeah, like this guy right here, page 229. So he has, you know, see if I can zoom in a bit. This is, you know, from Frankel, and he has these formulas that apparently Gauss derived and so forth, and mentions that these are actually Gauss's equations, and the second are by Kodazzi and Peterson, and he also mentions that these equations right here, 8.34, are so-called integrability conditions, and if they're satisfied, then the two matrices which are, if they're satisfied with two matrices which are given, then those matrices can serve as the first and second fundamental forms for a surface in R3, and they also mentions that Bonnet showed that these conditions are sufficient to ensure the local existence in R3 of a surface having those prescribed first and second fundamental forms, which I think is interesting. Wait, let me get back to the relativity here. That's just a little bit of geometry, because I think it's worth a second here to just sort of grossly indicate how this wild world of Riemann tensors and curvature and everything connects back to our humble study of surfaces in that previous course. All right. Now, although I don't know. I mean, I don't think I'm going to give you a genuinely. I mean, I might have a four-dimensional manifold I'm calculating the curvature of at the end of this lecture. But I think the truth is, the calculations are kind of two-dimensional. And to do a genuinely gnarly four-dimensional curvature calculation, yeah, it's more involved. So anyway, moving along here. So again, we're still following Frankel at the moment. He puts forward the following definition. If M is a manifold, and a fine connection or a covariant differentiation operator is an operator, nabla, that assigns each pair consisting of vector x at the point P and vector field V defined near P a vector, nabla xv, at P which satisfies the following conditions. Linearity in sort of both entries, right? And also a product rule here. This is the Leibniz rule, right? So, and it's for all vector fields V and W and functions f and real numbers a and b. Moreover, if x is a smooth vector field, then nabla xv is also a smooth vector field. So, at first glance, this does not really look much like what Carrol does, but we'll circle back eventually. So just stick with me here. Sorry, I'm trying to find a spot to put my papers. I got too many papers. All right, going on here. So let's see here. Suppose that you've got a frame, right? So a frame, that's just a basis for the tangent space, all right? And sometimes I think about it at a point. Sometimes I think about it as being, a set of vector fields which serves as a basis over some, domain, point-wise. But in any way, if you have such a frame, you can expand a vector in terms of that basis, like so. And then if we were going to calculate the covariant derivative with respect to the vector x, we could expand it in terms of covariant derivatives with respect to the frame, like this, right? Contracted across the components of the vector, like so. So it does make sense to focus on the nabla E sub I, all right? Which essentially is where Carrol focuses his attention almost exclusively. But anyway, let's see here. So the commutator of vector fields, x bracket y, which is defined as such, so it's a composition of operators. And at first glance, you'd think, well, if I take the composition of two differentiations, I don't get something that satisfies the product rule. If you've studied the second order, like d squared dx squared, it does have a product rule, but it's not the Leibniz rule. It's something a little bit funkier. And yet, this does turn out to be actually just a derivation, because the second order pieces cancel due to the anti-symmetrization here. So it's not entirely obvious that that's a derivation, but you can prove that this is in fact a derivation, meaning it's linear and it obeys the Leibniz rule, which makes it a differential operator, which makes it a tangent vector, since we sometimes like to look at tangent space as the set of derivations at a point, right? Anyway, I will mention this. If we had that our frame was actually a coordinate frame, right? If it was actually a coordinate frame, then because of the commutativity of the partials, we get that the commutator is straight up 0. And in fact, if a frame has commutator 0 pairwise, then for all ij, well then actually there exists coordinates for which there exist coordinates for which the frame is the coordinate basis for that frame. Let's prove that. So the proof is kind of pretty. I don't prove too many things in here, but I'll prove that. Here it is. So a frame E is locally a coordinate frame if and only if the bracket of every basis element in the frame is 0 with another one. So the commutator brackets of all distinct members of the basis have to be 0 for us to understand that the basis is in fact a coordinate frame. So the forward implication I just discussed on the last page. Here's the reverse implication. Suppose you have that the brackets are all 0. And then let sigma 1 through sigma n be the forms which are dual to E1 through En, right? Dual in the sense of, what do I mean? What do I mean by dual? Remember? So that just means that sigma I of Ej is Kronecker delta Ij, right? So the dual frame, right? And we can do that. And well, the interesting thing then is that if we look at the exterior derivative of the dual frame here, and let that act on Ej comma Ek, well then there's an identity that's known for the differential of the one form acting on a pair of vectors. It's the one form acting on the commutator of those vectors, but the commutator of those vectors is given to us to be 0, which then shows us that in fact the differential acting on this pair is 0. But since this is an arbitrary pair of basis elements, this implies of course that the differential of sigma I is 0 for all inputs in 2 dimensions. I mean, not 2 dimensions, but 2 inputs. And so d sigma I is equal to 0, and that's true for each I. And that means that this is a closed form. And at least locally, we can say that closed implies exact. In other words, there exist coordinates or functions on the manifold x1 through xn for which sigma I is dxi. And how do you know that those functions are independent? Well, you know those functions are independent because the wedge product of the differentials is the wedge product of the dual basis forms, which, by the way, this is given to be non-zero because of the way in which they were derived. This is something you can prove. If you take a frame and you find its dual frame, then the wedge product of the dual frames must be non-equal to 0, because otherwise you would imply a linear dependence amongst the dual frames, which would then violate the initial linear independence of the frame that we started this whole ball of wax with. So then the coordinates are independent, and voila, that means that the frame is partial x, EI is partial xi for each I, and there you have it. If we have the brackets are 0, it implies it's a coordinate frame. So it's pretty cool. Yeah, so there are really I would say there's sort of 2 different ways to scratch this itch in terms of deciding whether or not either vectors or forms describe a surface or something. One of them we can use these commutator brackets. The other way is to use wedge products of forms. I don't want to say much more about that. I'll just say that that's something to kind of think about. There's dual viewpoints. And you can see this most concretely and explicitly laid forth if you study the different versions of the Frobenius theorem. There's a vector field formulation of the Frobenius theorem. There's a differential form formulation of the Frobenius theorem. And they both are different ways of capturing the same linear algebra. Anyway, okay, back on track here. So if we want to calculate the covariant derivative, we can write formulas for the covariant derivative in terms of a frame, right? Now the frame doesn't have to be a coordinate frame. It could be something else. And so here's how it goes. I just expand in the frame and pull out the xj using the linearity, and then I break this up into the two pieces using the Leibniz rule for the covariant derivative, and then we introduce what are called connection coefficients over here. See, the connection coefficients tells you basically how the kth frame changes in the jth direction in some sense. It tells you how the frame is rotating into itself as you take the covariant derivative in the frame direction in this way. There's a sum over I here, okay? So these are the connection coefficients. In the special case that this is what's called the metric connection or the Levi-Civita connection, then these will be Christoffel symbols, and we have that uppercase gamma notation for them, okay? But more generally, they don't have to be that. Okay, so let's talk more about this abstract frame here for a bit. So here's this just lovely calculation, and so we find out that we can write the formula for the covariant derivative a few different ways in terms of the frame basis. And if you look at this, you can kind of see that we can eventually pull out the vector field and say, oh, okay, so it's really the covariant derivative is this thing acting on the vector field to give a new vector field, right? Something like that. So, that these formulas are interesting. I'm not sure they're terribly useful to us at this point, but I just point them out because you might wonder how you could do something different. Well, here's how you could do it different. And okay, so we got to this point. Actually, we got past this point, then I went back to this point here because this is really the formula I wanted. And basically, if you peel off the coefficient of EI, that gives you the upper ith component of the covariant derivative of v with respect to x, like so, and then the formula for that is straight up this. So you see that and then, well, furthermore, so that we're still talking about the covariant derivative with respect to x, but really to make contact with what Carrol does, he doesn't really look at the covariant derivative with respect to x, he looks at the covariant derivative with respect to, like, partial xj down here, and he's going to call that nabla j. And so if we had coordinate basis, then we could write this formula for the nabla j of vi, which would be the ith component of this thing, and we're going in the direction of partial xj, like so. And then some other books use a semicolon notation for that. I think Frankel uses this slash notation for the covariant derivative in the coordinate direction, to each their own. All right, let me forge ahead here. There's this sort of unending drink from the fire hose of duplicitous and sometimes unnecessary notation, but we'll get there. I'm about to say something non-trivial. So here we go. So one of the interesting calculations that you might try is what happens if we take the covariant derivative of a covariant derivative, right? So if I take the covariant derivative of a covariant derivative, well, then I have xj here, and then I'm calling w the covariant derivative of v with respect to y. So that give me that. And then now here wi is this right here. So then I have to plug that in here and then there. And then I'm just going to point out that there are certain terms here we can find, right? Like xj, ya, vb, partial j of the connection coefficients wabi. And likewise, there's this xj, ya, vb, and then product of the w's. Product of the connection coefficients from over here, omega times omega, like that, right? And then there's a bunch of other terms, right? Or other terms. And similarly, if we do yx, we get the same kind of terms, but with, with x and y flipped over. Then if I relabel the sums, as I do on the last step here, relabel my a to j and my j to a, and likewise over here, then you notice I get very similar looking terms here and here, but the indices are flippity flopped, right? You got like a JAB here, you got AJB down here, you've got JKAB, up here you've got AKJB, and then there are other terms, right? And then if you were to look at those other terms and tilt your head and squint, stare at them for a bit, you'd be able to see that a lot of those terms would cancel out if you took the difference, and that might lead you to look at this. So here it is, theorem. So you've got vectors x, y, v at a point P, and look at their extensions to some neighborhood of P. Then you can define r, x, y, v as the difference of the commutators, the difference of the covariant derivatives successively taken minus the covariant derivative of the commutator of x and y, all right? And so I haven't quite showed you the proof of the whole theorem, but like a good bit of the calculation is what we had on the previous page. And you can kind of see it from what I've done a little bit. If you look at here, like what I'm trying to say is like what I have, so the theorem is claiming you can take nabla x, nabla y, minus nabla y, nabla x v, right? And if you look at the calculations I did here, right, you see where these terms are coming from. Like you've got the partial derivatives of the connection coefficients, right? And you've got this anti-symmetry and same kind of indices, but slightly skew. If you look at the pattern, you can match the pattern here and here versus here and here versus here and there, and we're subtracting one from the other. So, and then somehow these other terms either cancel out when you take the difference, or they're put in order, let's say, by this term over here, the covariant derivative of the commutator. So that would be a longer calculation to actually prove this theorem. But I believe it. I've seen I think I've done about 40% of the calculation there, maybe. Maybe that would be a good homework problem. Maybe. You can dive in and fill in any detail that I haven't done in here, and I think that would make a good homework problem. Let's see here. So, yeah, so we look at this, difference of covariant derivatives, and because each one of these things is a vector field, that makes this collectively a vector field, and as such we've defined a vector field, and because of the way that the vectors x, y, and v appear here, this actually defines a multilinear mapping with 3 inputs and a vector valued output, which means it's really defining a tensor of a particular type. But of course you can fix a pair and look at how v maps and look at it as a linear transformation from the tangent space at P to the tangent space at P, and you can call it the curvature transformation. And now Frankel says this is a fourth rank tensor. It seems like that language has gone out of favor now, because we often like to use the word rank as it regards to like linear algebra, the concept of ranks. I try to use the term type rather than rank, but the rank is like this. So if you have a type KL, K plus L would be its rank in this language, right? But anyway, this is theorem 9.10 from page 244, Frankel. And you can also see here that we have that anti-symmetry of the final pair of indices in the curvature tensor here, so defined. Also, Frankel mentions if we're given vector fields x and y, we can form the Lie bracket. This is also called the Lie bracket, by the way. And the anti-symmetrization, the difference of these covariant derivatives like such, these are vector fields, and their difference gives something we call the torsion. Torsion as a vector value 2 form, here it is, and it turns out that the formula for this just works out to the difference of the connection coefficients, all right? and so with the lower indices commuted. So if your connection coefficient is symmetric in the sense that omega ijk is omega ikj, did I say the same thing? Ijk versus ikj, right? They're equal. Well, then this is 0, and then you've got a torsion-free or symmetric connection. And it will be the case for the Levi-Civita connection that we almost always use. That is an example of a symmetric connection. All right, so continuing on here in my brief tour of some of the fun ideas from Frankel. The last few pages we've been exploring the general theory of affine connections. Our true interest, of course, is in semi-Riemannian manifolds. And we want to write theorems that make full use of the metric on M, all right? And so, essentially the main order of business here is to define parallel connection, parallel transport, right? So here's the definition: a vector field y along a curve is parallel transported to the curve if, when you calculate the covariant derivative of that vector field with respect to its velocity field, you get 0. So that's a fancy way of saying that the vector field stays constant with respect to the curve, as is judged by changing of vector fields with respect to the connection, right? Because the connection basically sets up a way of measuring the change in vector fields from point to point, right? So once you've defined some sense of how things change, it makes sense to say, oh, the vector field doesn't change with respect to its velocity direction. So in parallel transport, we expect the length, what do I mean length of what? Length of y and z, talking about those ones, the length of y and z, and the angle between y and z to be held constant throughout the transport, all right? So that's what we would like. Now, that doesn't have to be the case. You can talk about connections that aren't metric, all right? Connections which don't respect your notion of length and angle, right? And it might preserve something else. I mean, I've never seen a concrete example of such, but you could. At least I don't think I have. And so here's the theorem. On a Riemannian manifold, there exists a unique symmetric connection satisfying this condition right here. And so this condition, notice that if this being 0, what would that mean? Well, let me circle back to what this means in a bit here. But so there exists a unique symmetric connection satisfying this condition, and for any pair of vector fields defined along the parametrized curve, and moreover, this is the Riemannian connection, all right, meaning that they're in a coordinate frame. You can actually write omega ijk is equal to gamma ijk, where the Christoffel symbols were formulated on 2. Now, I realize I wrote the formula on page 2 for a surface, but that same formula would hold in a higher dimensional manifold. And don't worry, we'll derive it again here in just a second, so let's get to it. So here's the proof. We consider the kth coordinate curve, where you have the parameter is t equals to xk, right? So if you differentiate with respect to t, that's taking the partial derivative with respect to xk, actually. And notice that x bracket y is really gij contracted across xi yj. And we're assuming that we have this condition on the connection, because remember the covariant derivative here. This is the covariant derivative, or sometimes called the oh goodness, what do they call that thing? Golly, it's the derivative along the curve with respect to the connection. Anyway, whatever the name of this thing is, anyway, this is the assumption of the theorem, and then so if we take the partial derivative of this guy, then that's going to be equal to this plus that, which in coordinates is like that and that, all right? And then I just take the product rule here, which of course has 3 terms, and over here you've got 1, 2, 3, 4 terms, I suppose. All right, and it just so happens that after appropriate, just tilt your head, squint, relabel indices perhaps, maybe not even that, this cancels with that, and that cancels with that, which just leaves us with partial k gij, this equal to this plus that. And that then, since this holds for arbitrary x and y, we can drop it and just read off from that partial k of the ijth component of the metric is equal to the contraction of the metric across the connection coefficient plus the contraction of the metric across the connection coefficient with the indices written as I have. Again, I'll make the definition that Frankel made earlier, which was to call the sort of define lowering the index for the connection for the convenience of this argument. And so we have this, and this would be analogous to my star equation, I think at the bottom of page 1 or top of page 2, I can't remember. And lo and behold, if we take this plus that minus that, I'm using the, I decided to go back and use the same indices that I used on page 2 just so I wouldn't go nuts. And have to reinvent the wheel in terms of the pattern here. But so when you do that, then you get the same cancellation that we did back on page 2, which leaves you these two guys, which then when you write it out, gives you these two. But now, if we're assuming the connection is symmetric, and remember, we didn't, the coefficients we introduced on page 2, those were symmetric just because we were talking about picking off components of the acceleration, right? This is not quite that. This is a little more abstract. So, like, I don't know that this has an explicit connection to the acceleration anymore, right? Could in a certain context, but it doesn't have to in general. And anyway, so if these are symmetric, I can add these two together, and I get twice GRU, omega upper R mu beta, like so. And then, if I use the inverse metric, which is the metric with the indices up, then I can kill this off and turn that into a Kronecker delta and get the next equation down here after some index relabeling, I suppose. But there it is, and the half, of course, comes from dividing the 2 to the other side. And there it is. That is the formula for the Christoffel symbols in terms of the inverse metric and derivatives, first derivatives of the metric. And notice the pattern here. It's not how I want it. I always write this term first. It's much prettier if you write this term first. You write this one, then that one, and then that one, and you can see that it's like the cyclic. It's like the cyclic reordering of indices, but it's plus plus minus. I don't know anything else right offhand which has this plus plus minus pattern. It's truly bizarre. Anyway, okay, so just to try to finish up on Carrol here, Frankel here. Frankel is a wonderful book. There's so many things in that book. Let me just tell you a few of them. So he has some historical comments. He mentions, and you know, I think these things are probably also mentioned in Carrol, some of them at least, but anyway, so Riemann introduced curvature in 1861. Right, and that's actually also where he gave explicit formulas for the curvature tensor, and in so doing he introduced, so up to that point non-Euclidean geometry had been studied, but primarily in the hyperbolic context, and also a lot in the formal context of, hey, what if I logically take Euclid's axioms and replace them with slightly modified axioms? This is still a logically consistent, thing we can play with. And so Riemann introduced the curvature tensor, and also alongside this same time period, he introduced models of manifolds that had what we call elliptical geometry where the curvature was positive. We might call them spherical geometries, right? And not just one, like as many as you like, pretty much. But Then Christoffel introduced covariant differentiation in a Riemannian manifold in 1869. And then a little bit later, Levi-Civita, Heisenberg, Weil systemized the concept of a manifold and a fine connection in around 1917 to 1918. Keep in mind, in 1915, Einstein had already written like the field equations from physical principles. And so I think essentially what happened was the idea, the whole framework, right, with the metric connection and the Christoffel symbols, that was all developed first because it's most natural to be tied into the metric structure, right? And then a little bit later, the more abstract affine connection idea was introduced here by these dudes. Anyway, a few more things. In a Riemannian manifold, one can introduce local coordinates y such that the metric is, this is a metric with constant coefficients, right? This is just basically the Euclidean metric. That's possible if and only if the curvature vanishes. Now here, theta is the curvature form, which we have not really, well, here's the formula for it down here. And also another theorem in Frankel, that EB an orthonormal frame field on a Riemannian manifold with dual frame sigma. The Riemannian or Levi-Civita connection is the unique matrix omega of one forms that satisfies d sigma equals to minus omega wedge sigma, and it's antisymmetric in that sense. And there's also a curvature 2 form, theta, which you can define as d omega plus omega wedge omega. This is all matrices of forms, all right? And like here's the details in terms of, this is like a matrix multiplication / wedge product kind of thing. And then the curvature form, it is a 2 form which is constructed from the Riemann tensor in this way, all right? Now, I'm not going to get into all that, except just to tell you, hey, it's here, and to mention to you that page 247 to 267 of Frankel developed this differential forms centered treatment, and alongside it, parallel transport, covariant differentiation, the whole deal. And I'm pretty sure this is all due to Cartan, and we've seen the 2-dimensional version of that in our differential geometry course because that's kind of the whole point of the book by O'Neill, right? But there is a 4-dimensional version of it, and it is in Frankel if you want to look at it. And it may also well be in an appendix of Carrol. I'm still coming to terms with the appendices in Carrol, so, you know, stick with me here. So up next, we're going to flip back to Carrol and study covariant derivatives and all that from his perspective, all right? So I think this is a really good place to stop the video and start again, so I'm going to do that right here.